Each k sub I generated in the key schedule is going to be mixed with the plain text with the same sort of mixture that we're showing here. This mixture is called the Feistel structure. At every step, we're going to have 32-bit halves that originated from the plain text. So at first, it really is just the high and low parts of the plain text. We will keep mixing these up, and in general, we have these 32-bit halves that eventually will stick back together as a 64-bit result. When we take one of these 32-bit halves, the right half is just going to be fed right over to the left half of the next round. So not much happens to those bits now, but they become left where more exciting things happens to those bits in the next round. The left bits, meanwhile, get fed to the right, but not directly. Before these left bits are sent over there, they're XORed with the result of this function f, where the input to the function f is both the number from the key schedule and the right-hand side. So the left and the right are getting mixed up by XOR here, while the right is getting also mixed up with the key through this function f. This function f is not like XOR at all. It only goes in one direction. So when you get the result out here, even when you know one of the inputs, you can't go backwards and directly reconstruct that right-hand side. The one-wayness of this function, which is hardwired into DES, that is where we get the encryption from. Having mixed up the two halves of the plain text this way, then we take the two new halves and feed it through the same kind of thing again, using the next key in the key sequence, until by the end we're using K15, and now we have two halves that we put together as a ciphertext. This ciphertext, due to the one-way function f here and the mixing with XOR, is not going to look like the plain text at all. How then will the receiving side that needs to decrypt this message go from the ciphertext back to the plain text? It will only be possible if the receiving side has the same key and thus generates the same key schedule. Let's see if we can work backwards just from these two pairs here back to these two pairs. Getting R15 is easy because it comes directly from L16. Getting L15 is not quite as obvious. We have to reverse the XOR here. Well, that's easy enough. We just reverse an XOR with R16, but we need to know what comes out of this arrow, coming out of our function f. We know the K15, that is an input to that function. Oh, but we also know the old left, which is the new right, which is the input here. So in fact, we can compute the result of this black arrow here, XOR it with the old right-hand side to get back to the new, for the decoding going backwards, the new left-hand side. This process of going backwards may look like it's a different calculation. It turns out, in fact, that this backwards calculation is the same as the forwards calculation. If we just take a forward end step here and compare it to a backwards end step, those look like they have different shapes. But let's flip around k, moving it to the top of f, and then let's twist the inside of this structure around without breaking any wires, and voila, you see it's actually exactly the same shape. So it turns out that going backward to decode the ciphertext is exactly the same kind of function that you use forward to encode the plain text. It's just that when we start from the ciphertext, we start with K15 and work our way back to K0, instead of starting at K0 and working up to K15. So overall, it looks like this. Encoding goes from the plain text using K0 through K15 to the ciphertext. The ciphertext goes from K15 back to K0, but otherwise they turn out to be exactly the same function, so we only have to have a single implementation of it that's parameterized over the direction of the key schedule.